friends, we're going to study today many other properties of water which are also very interesting and very practical. So I'd like your attention again. This is a picture which I take with my camera with the speed of 1/4000 of a second. Now you can see here a drop falling, and you can see it's like a hole in the water, and as you can see also on the sides you can see like wrinkles, and you can see also the bowl is full of water and it makes like a meniscus, like a little hill. Why water at the surface is getting like this little hill? Why is get convex, right? Why it's like a hill? And why when the drop falls, instead of going down straight and sinks, like if you throw a little ball in your dirty washing, it's not gonna splash anything, it's gonna go straight into a dirty washing in your washing bowl. Why the water splashes? Why is doing that? And you remember straight in the start I told you that you're going to learn how iron actually can float. It's actually iron, which is more dense than water, may float. If you take a piece of iron, solid iron I'm saying, and throw it in the water, it's going to sink. Everyone knows that. Now, but I'm going to show how can you take a solid iron and actually can float. Now look at this picture now. Here's an iron, right? It's a needle, solid iron, but it floats on the water. What's going on here? Why it floats? And you can say, but that is just a needle, it's too small, blah, blah, blah. Well, let's take a razor. Put it in the water, the razor also doesn't sink. Did I put anything in water? No, it's a pure water from the tap, the one that you have. I didn't put anything in the water, I didn't increase pressure of the air, I didn't do anything, just plain water. So why the needle and the razor is actually floating? Now, do yourself a favor, do this experiment at home, your children is going to enjoy it. You take a needle and put it in a piece of cigarette paper, or a very thin paper, or you can put it actually very carefully on the water, and if it's on the cigarette paper, I'm talking the paper not from the packet of cigarettes, a paper from the cigarettes itself, just the paper. You put it there, it's gonna get wet and the paper is gonna sink. Now, but the needle is gonna stay. What on earth is going there? Is the paper heavier than the iron? No, not at all. Just the iron doesn't get stuck to the core and wet to the core like the paper does. And when the paper sinks down, the needle or the razor is going to stay there. We're talking solid iron. Look now, the ships that we saw last time, they're iron, but they're not solid. They're like a ball, and actually this is why they float, because the volume of water that they take, it's actually the volume that they take in the water, it's actually more than the volume of the water that they displace, and this is why the ship floats. If you've got a ball of iron, big ball, and put it in the water, it's gonna float. This is why the ship made of iron, you can see it was iron because it was rusting. It stays there. This is solid iron. Why then it's not sinking? Wow, what's going on there? This is the lesson of this lecture, and this is what we're gonna study. If you didn't know it, it's called surface tension. What is surface tension? Now look at it. We've got molecules in the water. We studied that, and the molecules get attracted to each other with hydrogen bonding, which is the stronger dipole bonding. And each molecule gets attracted to the next one in all directions when it's inside the water, inside, not here, inside the water. not on a surface. That's very important. So they get attracted to each other. So all of the forces cancel, so the molecules stay put. Now, when there is a molecule at the surface, now there is no molecules of water on top of it, so they experience only forces at the molecules on the side of it, as you can see there, and beneath it, under it. So now what's happening, because of these forces, the molecule and the molecules, the bunch of molecules that are there, they try to stick together and they actually take what shape? Look now, if you've got all of these forces acting together and a lot of molecules, you're going to have a ball shape. This is why when you drop water, it turns to a ball, because all the water now, there is nothing on the top, on the bottom, all around the water. So the water gets these forces there, acts in such a way that the water gets tied to each other at the surface, and this is why they get ball shaped. This is why the planets actually are ball shaped. This is why the sun is ball shaped. This is why when we drop water, it takes ball. This is why it rains in a drops which are small balls, because there is no forces to pull it on the other side. So it takes only the surface, and under that surface, so it takes all of this, look at it, nicely ball shape. So this is called surface tension. The water gets tense on the surface because the molecules get together, gets pulled together on this direction and pulls together down. So they get pulled together. So now this comes like a film, like a blanket on the top, which you need a force to break it, because it's a strong hydrogen bonds here, just like here. But the hydrogen bonds are only in a certain direction, not in all directions. So I've got very strong hydrogen bonds here. We said the water experience very strong hydrogen bonds. The strongest hydrogen bonds, because you've got two lone pairs which are get connected to two hydrogens, very strong hydrogen bonds. So now these hydrogen bonds have to be broken so that the needle must fall down. So I've got two forces now, and let's see the forces of the needle if we look at sideways. Look now, you've got the gravity which pulls the needle down. We're looking sideways now, the needle, not across the needle. So now we've got gravity which pulls, but then we've got hydrogen bonding, like I showed you on the previous one, which sticks the molecules together and don't allow they to get broken. So you need force so that the needle can sink. Now we've got these forces actually, that this hydrogen box actually pushes the needle upwards. This is why it floats. Do you understand the beauty now? That's physics. Now this is what's called surface tension. This is actually what is the surface tension, and this is why we've got floating. Otherwise these objects won't float. The needle and the razor. So now when the surface tension, the hydrogen bonding, is strong enough to create a force and is stronger than the gravity, the needle will float. If the gravity gets heavier, if you take a marble or you take a ball, glass ball or whatever, it's gonna sink, because the surface tension, the hydrogen bonding, the strength of the hydrogen bonding, the attraction that's created between the electrostatic forces is not enough to overcome the gravity. Then the gravity takes over. But in this case, the hydrogen bonding forces, the electrostatic forces between the molecules, they get stronger. This is why it overcomes the gravity. Now I'd like to show and ask you a question. Now, what will happen if we have not room temperature water, but we've got boiling water? Will the needle sink? Same room pressure, same needle, same thing. Will the needle sink at 90 degree water, or will the needle float again? If yes, why? If no, of course, why? Everything is why in these lectures. Simply because we're not here studying some nebulous thing. Everything we need to know why this is happening. And we're gonna dig so deeper until we can. As much as you can. So our knowledge here is going to be as good as it gets. I promise you. I enjoy that, and I'd like sharing it that with you. Press the pause. Okay, the reason is, if you give this answer, you're right. We studied before, you should be able to give it. What's happening at 90 degrees? At 90 degrees and above, and even under it, some of the hydrogen bonds get weakened, because now the water starts moving faster, and when they move faster, the hydrogen bonding cannot form, and cannot form so good as it was on the lower temperature. Because of that, now the gravity is not balanced now by the hydrogen bond electrostatic forces, so it's going to sink. We don't have enough these surface tension forces. What's happening? Why? Because hydrogen bonds gets destroyed, and it's not recovered much faster as it's in a room temperature water. Now if you're gonna try it with 90 degrees, don't put it with your fingers because it's gonna get scorched. You need to put it with the help. Or you can put it with your pincers or whatever. Just put it, and you're gonna see it's gonna sink. Another thing I want to ask you, another question. Always questions to make sure that you know it. This is ethanol. Ethanol is alcohol. Right, you can have a medical alcohol and you can try it. This is the ball and stick figure of ethanol. You've got one of these structures, so we're gonna have hydrogen bonding. My question to you is, if you put needle on the alcohol, is it going to sink or is not going to sink? Press pause. It's going to sink simply because you don't have such a strong hydrogen bonding as with water. With water we've got two hydrogens connecting to one oxygen atom in the lonely pairs. We're not talking about here the molecule. We're talking about intermolecular forces. We've got hydrogen bonding, which is 2 times stronger than this one, because this is only 1. All right. Also, you can see here this bond is only 1, and the lonely pairs can get connected only to 1 hydrogen. But you said, no, you've got these methyl groups and you've got a lot of hydrogen. Yeah, why this hydrogen is not connecting? They're they've got their shell fully covered, so they're not gonna get connected. They're busy with the carbon atom here, and same one here. They're busy, so their valence shell it's filled. You see, so they're not gonna react with this oxygen. But the oxygen of the water get 2 lonely pairs. They get connected with the hydrogen, with the other molecule, with the hydrogen bonding. This is why if you put a needle on the ethanol or a medical alcohol, it's going to sink. That's the whole point. Now look at this picture. Have you seen such a thing? So now in one of the tubes we've got mercury, and in the other tube we've got water. Why the meniscus on mercury is convex, but the meniscus on the water is concave? Why one is making one way, but the other one, both are liquids? Why it's like this? What happened? That's a result of the surface tension that we studied. Water has bigger surface tension than mercury, and because of that, when it touches the glass, all right, when it touches the glass of the tube, it's actually, the molecules start pulling one by one each other, and it goes up, and it goes up. While the mercury, also you've got this surface tension, but the mercury is much heavier than the water, so the gravity pulls it down and actually makes convex meniscus rather than concave meniscus. Now, the mercury also doesn't make such a nice contact with the glass. Well, the water makes nice contact with the glass simply because mercury, as an elemental metal, doesn't have polar covalent molecule like the water have. So now when the water has polar covalent molecule and the tube is made of silicon oxide is also polar molecule. Do you see? So now the polar molecules get together and they get strong adhesive force, adhesion. Now I've got two forces here. Like in the needle floating on the water, we had two forces. Now I've got also two conflicting forces. The first is adhesion. That means the connection between the water dipole forces between the tube made of silicon oxide and the water made of hydrogen oxide or water. They are both polar, so they get dipole connection, and this is why the water gets stick to the tube. If you empty both tubes, you're gonna see that is gonna be wet, and this one is not gonna be wet with the mercury, but you're gonna have a small beads of mercury, and you're gonna see it's also around like a small droplets. You've got some adhesive force, but it's not so strong to overcome the gravity. This is why the gravity pulls it down, and it becomes like a ball. Like when you throw a drop in the air, it's gonna go ball. So it starts shaping this ball shape, which the planets are also balls. Our Earth is ball, the sun is ball, and so on. So the stars are ball, the planets. So now, what's happening with the water? The water also have adhesive force, so it sticks to that, and that force is the result of the dipole-dipole connection that we said. So it's so important to study that in the previous lectures. And then you have cohesion of the water. Cohesive force, the force between the molecules itself, between the hydrogen bonds between the molecules. Right. So this is two forces. If the adhesive force was stronger, the water would have flied away. But now we've got also cohesive force that keeps it away. So this is why the water doesn't fly away. And this is why it sticks there, but you've got some of the adhesive force stick to that. This is why I've got this meniscus. Now, what is the adhesion force with the mercury? Please press the stop and tell me. You should know that. That is the metallic lattice, where we said that the mercury is a metal, so that it is surrounded by a lot of electrons, and these valence electrons that we've got, they actually go all around the nucleus of mercury, and this is why it's metallic. Otherwise it wouldn't conduct electricity and wouldn't be so shiny. So when the light shining on that, the electrons that are moving reflects in this way. They start moving the light this way, we seeing it as shiny, and this way conducts electricity, and all metals are shiny and conduct electricity. So now the metal bonding inside of the same bond is the metallic bonding. The electrons push the nucleuses which are inside. We studied it, and this is why it stays metallic. And normally the metals get very high temperature of boiling. Why mercury is liquid then? We studied that. I'll just remind you quickly why it was. Because the mercury is a very heavy metal, got a lot of electrons, same like gold also had a lot of electrons. So these electrons start moving faster at the fraction of the speed of light. And we said that when you've got fraction of the speed of light, you've got one of the relativistic effects of that is increasing the weight. And now the electrons get heavier, they get closer to the nucleus, and now when they get closer to the nucleus, the valence electrons doesn't have so much strength to push all of this down, because they are also down. So they don't have strength so much as before to pull all of this together like with the iron. And this is why we've got metallic bonding with the mercury. And this is why the mercury is liquid. So you've got two forces. You've got adhesive and cohesive forces. So now, this is also responsible for the capillary action. The capillary action is how the plants actually suck moisture from the ground. Did you ever think about how can a big plant suck moisture from the ground and takes it away? What a pump is there? That's the capillary action. And we prove this by, look, we put these beautiful carnations. I love carnations. They smell so nice. God created the flowers just to show his love to us. You know, every flower, when you look at it, Jesus says, if God cares for the flowers so beautifully that even a Solomon in all of these riches could not dress so beautifully as flowers, how much is not going to care for you? Oh, of little faith, Jesus says in Matthew chapter 6. So don't worry about tomorrow, but first seek first the kingdom of God and everything will be added to it. So when you look at flower, we see it's beautiful and it smells beautiful. And this flower, look at it, if you put blue colorant in the water, we're going to see that the white carnation turns blue. Do you see it? What's happening? It's this capillary action. Now, let me explain what is capillary actions very, very easily and you'll understand it. First is the balance between these two forces, the cohesive force and the adhesive force. All right, this is the battle. This is why we see it, the convex form in the mercury, but concave in the water. The water starts rising up into the tube. Now look at it. You've got water which is connected to a different vessels. All of them in these 6 tubes that are there, they are different diameter. All right. So now what's happening? The one that is with the bigger diameter, they don't get so high as the one with the smallest diameter. Why so? Because the adhesive forces are much stronger. You don't have so much weight pulling down than the cohesive forces that are pulling it up. While here we've got more liquid and the cohesive force doesn't make it up so high as here. While here the cohesive force is much bigger than the gravity to pull it, than in this case, so it pulls it up. Now, you study physics, and in grade 5, they show you connected vessels, and the connected vessels look like this. And all of them, every single physics teacher is going to say that connected vessels, even if one is bigger, the other one is smaller, they're going to have the same level, and that's the physical law, because the pressure is exactly the same. It's a Pascal's law. That's physics. We study here chemistry. Now, even if you take a big drum of water and take a small pipe out of it, and you're going to see that the level of the small pipe and the big vessel, they are the same. They are absolutely the same. The quantity of the water is much bigger, but the pressure is the same. The pressure is exactly the same. Every square centimeter has the same pressure in the pipe. Say you've got only 1 centimeter square there, so you've got the same pressure as every single 1 centimeter from the bigger pot that we're going to connect. Or even if you put the whole sea, it's still going to rise only to the level of the pipe that is connected. So let's go to another property of water, and that property is actually one of the most important properties of water. This is why we can stay clean. And the point here is that the water is actually, God created it to dilute a lot of things, and created it actually as an almost universal solvent. It can dissolve many, many things. If it wasn't so, can you imagine the dirt that will be in a thing? So God gave us the water and created in such a way, with such a polar molecule, that it cannot get attracted to the dissolved particles in the water and obviously dissolve them and wash them away. This is why actually we stay clean, otherwise we'll get sick very quickly if the water didn't have this quality to dissolve particle in there. Now we're going to study the mechanics and all the quality of water that actually make it possible this to be dissolved. We studied a lot of them in the beginning when we did our basics and the intermolecular connections, dipole-dipole attraction, ion-dipole attractions, and also dipole-induced dipole attraction in the case of gases that are dissolved there. But we're going to explain it in detail. Now ask yourself why something is diluted. You've got two forces. You've got one force in the water, which is a hydrogen bonding that keeps the water together. Otherwise it wouldn't be water. As we studied, it will be like the hydrogen sulfide. The smell of the rotten eggs is going to fly away. It's going to be gas, but the water keeps together. So you've got strong hydrogen bonding. So you've got force between the solvent, and also if we put solute like salt, you've got very strong ionic bonding between salt, we said, between the chlorine and the sodium atoms. There is a strong ionic bond. Now we've got these two forces now. One force that keeps the salt together as a crystals, and the other one that keeps the water together. Now they get together, and now of the forces between the atoms and the molecules of the solute are stronger, it will never get dissolved in water. That's the basic principle. But of the forces of the intermolecular attraction between the solvent and the solute gets stronger between the forces of the solvent and the forces of the solute, it will be dissolved. I'll repeat that. If the forces between solute and the solvent are stronger between the forces of each one of them, in the case of salt, ionic bonding and hydrogen bonding, if that's the case, it's going to get diluted. If it's not going to get diluted. So the forces between the water and the solute must be stronger than it is. So now, when we've got this quality of the water, we know that very well it's going to be ionic dipole attraction, ionic dipole force, which we studied long ago, and we revised it in a previous lecture also. This ionic dipole attraction is the strongest of the intermolecular forces, and this is why the molecule of water attracts the salt, breaks the lattice, the lattice of the salt. The lattice energy is getting smaller, and the salt gets dissolved. This is why the water is universal solvent, especially with ionic compounds, which are the salts, right? Different salts. Now, and this is why the solution of any pollution is the dilution. I'll repeat that. The solution of the pollution is dilution. And this is actually what's happening to do it. And this is why we've got this ion dipole interaction that I showed you. All right, then comes a question now. We know very well that salt is dissolved in water. We know very well. Everyday experience, otherwise the food will taste bland if we don't salt it. This is why when we put salt in the food, it gets tastier, because it takes the molecule of the other molecules, and actually because of this strong electrolytes in the water, the ions of sodium and the ions of chlorine, they start conducting electricity much faster as we see the light shining, right, in the previous lecture. And because of this electronic movement, of this electric charge movement, actually the aromas and the different complex molecules that cause the food taste with different aromas, they get actually faster moved into our tongue and our senses of taste. And this is why when you put salt, the food starts taste better, because of all of this electrolyte of the salt that is there. These ions dissolved in the water now, they start transferring electricity much faster and transfer all of these molecules now, and the other ions transfer it to your taste buds and it tastes better. Now you know why the food tastes better when you put salt, and many other things. Just be careful with salt. Use salt. You need salt for your body, for your electrolytes, but don't abuse it. I'll tell you a case. I trained, and I want to be very shredded, to have very nice shredded body, and I did it by stopping the salt, because salt, when it's in excess in your body, actually holds water, because it needs to hold water, otherwise you're gonna get dehydrated and you're gonna die. So the salt in your body actually retains water and you get fat. And I said, no, let's take the salt out, and the water is not gonna hold so much water, so you're gonna have your six-pack and you're gonna have nice shaped body. But what happened now, I don't have enough sodium and enough chlorine ions in my body now, and according to Le Chatelier principle, which says that if you reduce anything from the chemical equation, the nature tries to produce it more. Say, for example, if the reaction is endothermic, right, that means it gets cool when the two elements get combined. Like, say, for example, the reaction of dissolving salt is endothermic. It's when it takes energy to break the lattice of the salt. So it's endothermic, that means requires energy. It's not exothermic, like releasing energy, like burning hydrogen and makes it water. The reaction of dissolving salt is endothermic. So if we put more energy, the reaction is going to go faster. Do you see? That's Le Chatelier principle. If the reaction is exothermic and releases energy, if you put energy, then it's going to go back to the reactants. It's not going to react. It's going to go back to the reactants, not to the products. You see? So what is happening in this case here? Why did I get high blood pressure? Just because of Le Chatelier principle. My body didn't have enough salt, but your cells need to have exactly very limited diapason of salt ions and sodium ions and potassium ions. If you've got one more, if you've got potassium ions, you die. This is actually the lethal injections that they put in America has potassium, and it actually reverses the polarity of the heart. So instead of plus, get minus, and the heart stops. All right. So more potassium, less sodium can kill you. So I had less sodium, and because I was eating vegan food, it has a lot of potassium. My blood pressure gets higher, otherwise I would have died. What the body is doing now, it's exactly Le Chatelier principle. The body starts reacting in a way that puts the pressure high so that the sodium can get, as much it was less in the body, I still got some sodium, otherwise I will die. The sodium will get higher because of the pressure now. And I get high pressure until it reaches 140. And I said, what's going on, man? I'm eating vegan food, I'm training, I'm doing all of this, and I'm with high blood pressure. What's going on? And then I start putting salt in the food, and now Le Chatelier principle start moving the products back to the reactants. Now we've got balanced equation. Now instead of the body to try to put more pressure, increase the sodium content, now the body, now you put salt, now you've got the reactants back. So now the body says, no, 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 I don't need pressure to push the product. All right, so the pressure is reduced, the body is reversing reaction. My blood pressure now is 115, 110 to 75, 74, like a schoolboy, and I'm 57. So that's the case of eating salt. Now, what's happening now? Why is diluting? We discussed it. I'll just revise it a little bit here. There is a lattice energy. We said with this lattice of sodium chloride, and when the water comes, it's actually the hydrogen bonds and of water molecule makes around that, and the molecule dipole, ionic dipole force of this that we studied, ionic dipole force start pulling the unit formula, the sodium ion and the chloride atom apart. So now the dipole ion force is much stronger than the lattice energy keeping the sodium and chlorine together. So now the crystal lattice gets destroyed, and now we've got ions surrounded by water when the oxygen goes to the sodium and hydrogen goes to the chlorine. Now this is how it happened. We explained that on the previous lecture with the Mr. Sodium and Mrs. Chlorine. Nicely explained. Maybe you can have a look there more. Now I'd like to ask you a question now. I always ask questions to make sure that you know what we study. This is lattice structure of stone, calcium carbonate. Now my question is, why salt get dissolved, which is also ionic compound. Calcium carbonate, stone, is also ionic compound. Alright, it's also ionic. You can see there is no covalent bonding, always lattice here. You've got calcium carbonate. Right. So you've got oxygen, you've got carbon, and you've got calcium. Why stone is not dissolved, but salt is dissolved? Both of them are ionic compounds. Right? Which you studied just now. You've got enough knowledge to answer it. Press pause. You can see here the lattice structure is much stronger and the lattice energy is much stronger than the ion dipole force. So now the water cannot cut from this structure. Do you see it? Because as I said to you, we're gonna have dissolved particle only when the forces between solute and solvent are stronger than between the forces that keep the solvent together, in this case very strong lattice energy, and the forces that keep the solvent together, in this case hydrogen bonding. So the ionic dipole, ionic being this structure, ionic and dipole is the force between this structure and the water is weaker than the force that keep the lattice energy and the force that keep water together. It's actually basically it's the strongest force is the lattice energy. It's much stronger. Now then next question arises, if that's the case, why oil is not soluble? Why oil is not soluble? Oil, there is a as you can see, that's the ball and stick figure of oil, and then you see ball and stick representation of water molecule. Now, why the oil is not dissolved in water? There is no lattice energy there. There is no ions. Look at it. Look at the molecule. How big is the molecule? This is triglyceride. Triglyceride means, let me explain you very quickly. You've got glycerol backbone, and you've got these structures. Yeah, this is why it's called triglyceride. And this is the backbone structure, and this is very long molecules. Very long, as you can see them. This is why it's called triglyceride. This is the oil that we're using in cooking. So, why the oil is not dissolved? This is not ionic structure, yeah? This is straight covalent structure. And as you can see, it's not polar, non-polar covalent structure. Right? There is no polarity in this molecule so much. You have got some oxygen atoms connecting the structures to the glycerol backbone, but that's different. You've got these three strands that makes it triglycerol, and you've got the water. So why the water doesn't dissolve oil? Everyone knows that. You see, I always was cross with my mom when she pushes me oily food. It was floating on the top, and I was very cross with her because I was a skinny boy, and she wants to make me maybe live more stronger. She makes the food oily to give me more energy. Maybe I don't know what was the reason, but why the oil is not dissolved in water? Now, you know enough knowledge to answer this question, and let's answer it. If you didn't guess it, let's answer it together. Now look at it now. You've got what kind of bonding between the water molecules? We said hydrogen bonding because the hydrogen gets bonded to the lonely pairs. So I've got two molecules of water bonded to one molecule, and that makes water very strongly hydrogen bonded to each other. This is what actually makes the water liquid. We studied that, we know it. Now here we don't have this hydrogen bonding. We said that the molecule is neutral. Huge molecule, but it's neutral. All right. So when the molecules are neutral, remember what was the forces there? We studied it. Please revise. That's the weakest force, London force. Dispersion, London forces. So what's happening is the electrons of this atom, when these atoms get together, they get attracted to the nucleuses of these forces temporarily, and they get attracted, and this is what they stick. But this is very weak force compared to this. You see, this is very weak force, but now it's weak force. It's much weaker. You got how many atoms? You got plenty, bigger structure, big structure. Now because it's bigger, the forces gets bigger. Do you see? Now the water cannot break this London dispersion forces. All right. So this is what's happening actually. The London dispersion forces. London and Hitler actually did the perfection of the covalent bond theory, and London discovered it, and the Hitler discovered the covalent bond, and both of them worked on the covalent bond theory. But this is only London dispersion forces. London is not in this case a name of a town, the capital of UK. London is the name of the scientists that discovered. And this is why we've got here this bonding, the dispersion bonding. You remember the halogens? Why the chlorine is gas, bromine is liquid, and the iodine is a solid? Because iodine has a much more electrons to disperse with the London dispersion forces, while the chlorine has very few electrons, so the dispersion forces are not so strong there. Well, here you see, look at it, what you've got here. So many. So now, this is not force that the water can break. And this is also non-polar molecule. So what is happening is, because it's non-polar, the water cannot make ion dipole. force like it did with the salt. You see? So this is what it is. This is what's happening. So now, this is why the oil is not get dissolved. We learned why the stone not get dissolved. We learn now why the oil is not getting dissolved. So now how we clean oily clothes, greasy and oily clothes, how we clean it? We need to find a way to clean it. So let's look at another big molecule. That's the molecule of the soap. Now what's happening in this molecule? Look now how huge is that molecule. Look now, and all of this is non-polar, like the oil, like the triglyceride. All of this is non-polar, so they don't stick together. But what makes the soap actually cleanses? You see, the cleansing action actually of the soap is due to the dual nature of the soap molecule. Now look at it, you've got the dual nature. It's a sodium stearate, don't worry about that. You've got one oxygen, and we've got one sodium ion. All of these are eager and willing to grab some hydrogen. All of this. This is the head actually of the big molecule. So I've got hydrophilic head because the oxygen and sodium wants to grab some hydrogen. All right, and you've got hydrophobic tail, but because it's so long, why the oil sticks together? Remember? Because of the strong London dispersion forces. So this molecule is going to stick to the oils, but this molecule, this part of the molecule is going to stick to the water. So what is happening is going to take the dirt. There is the dirt here, the grease, and you can see the hydrophobic tail gets stuck because London attraction forces, London dispersion forces get stuck to the grease because it's attracted. The hydrophobic is not attracted because it's hydrophilic. It actually sticks to the water because it wants to grab some hydrogen and get bonded to it. And because of that, the one gets into the grease and the other one gets into the water. So now it cuts it off. It's a strong force, cuts it off, and you've got small particle of dirt there. And this is why the soap cleans. You got small part of dirt and then we wash it. So the hydrocarbon tail is readily soluble in oily substances, which are non-polar. That's why big London dispersion forces. While the ionic head, OCO2 sodium head, actually remains outside of the oily surface, as you can see on the picture. When enough soap molecules have surrounded the oil droplet, then the entire system becomes stabilized in water because the exterior portion is now the largely hydrophilic, so it goes into the water, we wash it. And this is how the soap actually removes grease substances from surfaces like hands, dishes, and clothes. This is the things. The second reason why the soap cleans is not only that, but when the soap is added to water, what is happening is it reduces the surface tension of water. What means that? It means that, because you can see this long molecule that I showed, that long molecule reduces the attraction between the water molecule, actually start breaking the hydrogen bonds. It reduces it, goes between them and causes the water surface to become less tight. Right? It becomes less tight. And then when it's less tight, it makes it easier for water now, to spread out, not to keep tight at one place and push us down and make convex meniscus. And this is why, because you've got now molecules of sodium stearate with the long tail down, cutting these molecules all around, the surface tension gets released and the water gets released. This is why I try to put needle on the soapy water, or do it even better. When you put the needle on the pure water, make yourself a very strong solution, or just take handy or sunlight, liquid water dishwasher, and then put few drops, and you're gonna see what sodium stearate, in case of the liquid soap, is potassium stearate, is gonna cause going down. The liquid soap are made by with potassium, and the hard soaps are made, solid soaps are made with sodium stearate. So it falls down because there is no surface tension. You see, when it's reduced, the surface tension, it disrupts the surface tension of water when you put soap, and allowing it to spread, and it's finished. Now let's go to little biology at the end of our lecture, and to explain how our cells got the same double, dual structure. You've got hydrophilic head and you've got hydrophobic tails. Now that's little bit hard science, but I want to explain it to you. This is called phospholipids because you've got phosphates with choline at the head, which is hydrophilic, and you've got also diglycerid. Triglycerid was the oil. Now I've got diglycerid because you've got two structures here. This is why I've got diglycerid. It's not difficult to understand. So now the polar group here, that's the choline attached to phosphate there. It's attached also to this diglycerid. It's actually, this is why it's called phospholipids, phosphoric head and the lipid tail. So what's happening is this forms lipid bilayer, as it is here. Look at it, two layers. This is why it's called bilayer. Obviously the hydrophilic head is gonna stay away from the hydrophobic part. So the hydrophilic head is gonna stay away. This is why they get lined up this way. The hydrophilic gets away and the hydrophobic gets into the hydrophobic. So now I've got cell membrane, or the border of the cell. That's actually the fence of the cell, and the fence get attracted to the liquids in the cell. This is why they can start getting nutrition, different things in the cell, also viruses, by the way, bad, and they can take a lot of ions like sodium, potassium, and all other things in and out, some other stuff into the cell. So they open, it comes there, this opens also and goes there, and also the cell can be kept moisture because of this hydrophilic cell, and this hydrophobic keeps the cell with enough moisture, and keeps also there, the outside doesn't suck the moisture inside, you see. Now let me show you one of the biggest molecule, the molecule of DNA. That's the structure. Don't get scared by names and things like this. We're going to study only what concerns us, the water. Now this is, you've got 4 amino acids that creates your DNA and tells you that you're going to have that voice, then you have that eyes, and then you're going to have that hair, although I don't have so many. And my color and my bones and my height, everything is determined by these 4, can you imagine, 4 molecules. Can you imagine, this is the code. You've got A, T, G, and C. And A connects only with T, G connects only with C. And you've got hydrogen bonds here, as you can see, between these two. This is what makes the structure of DNA strong, but not so strong so that it can be replicated. It's a double hydrogen bond, that you've got here, triple hydrogen bond. Can you imagine what's happening? And then you've got sugar, which is connected to the strains of the DNA. There is it, A, T, C, and G. Always A, T is connected, and TNA, but not A with C. This is triple bond, this is double bond. There's the sugar, there is a phosphate. Sugar and phosphate makes this structure, and sugar and phosphate the other structure, and this is why I've got the double helix. And in between you've got the amino acids, and you've got the bonding. So when nucleic acid comes and tries to replicate this is opening, and start replicating one side and replicating the other side. Thanks God that God created these to be only able to connect it with T and C only with G, because now we've got code. You see, this code can be replicated. If it was random, it won't be replicated, but A can be connected only with T. So when you've got only one of the strands, we know that from A we're going to have only T. If it was C, G, and A, it will be Dermakar, it will be chaos. And you won't be able to replicate, but God created in a way that A created only T and C created only to connect with G. But you can tell me what this has to do with water. Water has extremely important function with the DNA. First, it gives a structural stability. Water molecules form a hydration shell around all of this structure, creating a network of ordered water molecules that stabilizes the double helix and helps forms these grooves. This, you see, two different grooves. One is small, another one is bigger. And these grooves is actually the replication, the code that will be replicated when the DNAs get replicated. Then you've got electrostatic shielding. Now, water molecules helps to screen the negative charges of the phosphate groups. I told you this red thing here is a phosphate, right? This phosphate is a negative charges. If it's negative, we know it very well, it's ionic. It's going to attract ions, and DNA may be damaged, and then you get cancer. All right, so now it shields, because now the water gets around it, like you remember, like which structure? Like a sodium chloride, like a salt. So it gets shells around it, so it's now damage is zero. It cannot get damaged. Preventing repulsion also between the two strands, because now if you've got negative and negative, you've got two things, right? You see here, there is a phosphate negative ion. If you've got negative and negative, they're gonna repulse, and this structure is gonna get teared off. So now it not only shields it from reacting from outside, but also shields them from repulsing each other from inside. And this is why it's beautiful structure. Now you see the miracles. Now I've got hydrogen bonding. Water molecules form hydrogen bonds with the polar atoms of the DNA molecule, as you can see it here, further contributing the stability and influencing his interactions with other molecules. That's very important. Now you've got hydrogen bonding. Not only inside, you've got hydrogen bonds also here, but it's also limited, so that can be only connected with what the molecule is going to influence the interactions, not what is just the chemistry. Everything goes there and connected to the phosphate here. Water molecules form these hydrogen bonds with the polar atoms. Then it's a mediator of the interactions now between all of this. Water molecules around this DNA react as bridges, facilitating interactions between the different parts of the DNA molecule, or between DNA and other biomolecules. Influences also the structure. Water interactions can affect how DNA folds. You can see it's folded and take shape, impacting his ability to interact with proteins and other molecules. And role in recognition. Right. Water molecules play a role in how DNA interacts with other molecules, as I say, influencing DNA recognition processes and biochemical functions. Thank you very much for your attention. See you next time.